How's it going, guys? Sorry I'm not there today, but here's the notes, and let's see how you guys do. I think you guys will do really well with it. Okay, so the first thing here today is we're talking about the Riemann sum, okay, Riemann sum. And before I just tell you what it is and how to use that to find area approximation, let's do this little discovery, and we'll use that to see what we get, okay? So let's start by drawing the following velocity graph for time being greater than 0. So I kind of made a little XY chart right here, and time is on the x-axis. And it says that v of t equals 5. So if v of t equals 5, that's going to be a horizontal graph at 5, okay? And that velocity is going to be going like this, okay? And it goes on for a while, right? And it always stays there because it's constant at 5. So the first question down here says, what would be the distance traveled after the first 3 hours? Well, you're traveling at this rate of 5. So if I think about 1 has passed, 2 hours has passed, and 3 hours has passed, this little rectangle that I can make that is being made by the hours and the velocity, the area of this will create the distance traveled. So the final answer is going to be 15 miles. Because again, if I'm traveling for 3 hours at 5 miles per hour or anything like that, I've traveled 15 miles. And the idea I want you guys to get down today is that when it says, what does this tell us about the area under a curve, okay, so under that velocity curve, it tells us the area is the distance traveled for this problem, okay? And for this chapter, we're going to be using area to help us find these pieces of information, okay? So this is the most simple where, hey, if I have a straight line, it's horizontal, and I have this time, right, I could just say, hey, this is just a box. It's just a little square of 3 by 5, so it's 15. Let's make it worse, though. So over here it says, now let's draw another velocity graph of v of t equals t squared. So let's draw a nice little line here, or x and y axis, okay? And let's graph this, okay? Let's graph that equation. So we have t equals 0, so 0 squared is 0. When time is 1, it should be at 1. When time is 2, it should be at 4. So 1, 2, 3, 4. And then at 3, right, it goes up to 9. So 4, 5, 6, 7, 8, 9. Right, and this pattern continues so that this becomes a nice U-shaped graph like this. Okay, and again, that continues on forever. And the question says below, can we find the distance traveled after 3 hours? So just like last time, we're going to say, hey, well, 3 hours goes up to this point, and we have the first hour, the second hour, the third hour. So technically, if I look at the area underneath this curve, that should give me my total distance traveled, right? Just like the last problem where I said area underneath is distance traveled. Here's the issue. This curve is really weird. I don't know how to find the area of this weird curved triangle looking shape. So can we find the distance here? No. It would only be an approximation, right? We could maybe do a little weird math and approximate what it would be, but we can't actually find it with what we know now, which we will in the future, okay? So how could we even approximate the area under the curve to find the distance traveled? And the big key for today is we're going to do something where we use rectangles. And you're probably thinking, what the heck are you talking about using rectangles, okay? Well, this is where the Riemann approximation comes into play, okay? And I'll get to this on the next page. We're going to use rectangles, okay? Here's what I mean by that. Is over here it says, using a right Riemann sum called RRAM with 3 rectangles, approximate the area under the curve of v of t equals t squared for the first 3 seconds. So I'm going to go back and copy that quick graph we did earlier, where this is 0, 0, this is 1, 1. This was 2, 4, 1, 2, 3, 4. And this is 3, 9, 5, 6, 7, 8, 9. Okay. All right, and I'm going to go back to this exact problem we did earlier, and I'm going to copy this because I'm lazy and I don't want to do it again. Okay. And we said for the first 3 seconds. So we have this area here that I want to approximate. Okay, this is where it gets fun. The right Riemann approximation method, which RAM, by the way, stands for the right Riemann approximation method, is going to state this. If I split this up into rectangles, I could approximate the area and guess it because everyone knows the area of a rectangle. It's just base times height. So the keyword right Riemann method is stating that I'm going to make rectangles that touch this curve in the right corner, okay? And what I mean by that is I'm going to make 3 rectangles where they touch the graph in the top right corner, which would be here for another rectangle and here for the third rectangle, okay? And if I find the area of this plus this plus this, again, it's not perfect, but it technically would give us an approximation of the area under the curve. And look at these little squares. This is a 1 by 1 square. And if I add that to a 1 by 4 square, which is here, and I add that to a 1 by 9 square, this will add up to an area of 14, and that area of 14 is these rectangles. This is our approximation. The issue with this is that this is not perfect because look, there's this stuff on top, which I don't need, right? I don't want that there. That's not supposed to be there. But because this curves and it's not a straight line, I can't find that. So technically, this is an over approximation. Okay, this is way more than what our actual area underneath here in green is. So the right Riemann sum is nice, not great, because it goes over, okay? Let's go to the next page and talk about something different. This is now called left Riemann sum. So the left Riemann sum, this is now going to be the left Riemann approximation method. Now this is a little bit different. I'm going to have the same graph as last time, just like this, where it has the curve of t squared, and it goes from 1 to 2 to 3. But now, this is where it gets a lot of fun. I want to make rectangles where the left corner of the rectangle touches this curve. Okay? And it has to be within this area. So here's where it's kind of nuts, is I need 3 rectangles, one here, one here, one here, that's going to go up and touch on the left. Over here, if I have a rectangle that touches this left-hand point, it's nothing. That's just 0. There is really no rectangle, but it has to touch on the left corner. If I touch the left corner here, that makes this rectangle. And if I touch the left corner here for this rectangle, it makes that. And these are my 3 rectangles. Again, it's the big one here, this medium one, and then this one that is completely flat because it goes to 0, 0. So looking at the area of each of these, this is 1 wide, 0 high, plus 1 wide, 1 high, plus 1 wide, 4 high. And that tells me that my approximation now is 5. But you guys know there's so much that we're missing here. We're missing this, and this, right? So this now is an under approximation. Right? This is way under, okay? So that method, again, it's nice to get an idea because now we know it's probably between 14 and 5 because we did the over approximation, the under approximation to find this area. But it's not perfect, right? And we need to get something that's a little bit more perfect, which comes down to our third way, which again, not totally perfect, but a little bit better. It's the midpoint Riemann sum. So this midpoint Riemann sum now, the MRAM, again, you guys know what this means now. It's the midpoint Riemann approximation method. We can now create our same graph as before, but now instead of the right corner of the rectangle touching or the left corner, now the middle of the rectangle needs to be touching, okay? So now my rectangles, the middle point, so what I mean by that is this point needs to be touching the curve as it goes through, right? That's why it's the midpoint Riemann method. So my rectangles here are going to be here. It's going to be in between here. And between 2 and 3, that midpoint's going to be like here, and it's going to pass through. So this is kind of good and kind of bad because even though it underestimates, it then overestimates over here. And because it underestimated this part, it overestimated this part. So it's a little bit better. And you're probably wondering though, Mr. A, how the heck do I know what height these are now? Because I know my graph is not perfect, this scale is not perfect. How do I know what height each of these are at? Well, luckily, that height is of the midpoint x value for each of these spots. So what I mean by that is this x value is half, right? It's between 0 and 1. It's the midpoint, okay? And to find the y value, you have the equation v of t equals t squared. So to find the y value here of what that actually is, that is half squared because I'm plugging into t squared, this. So that y value is 1/4. Over here, this x value is 3/2, or you could think 1.5. So the y value for that, again, it's not perfect, so don't say it's 2. The y value of 3/2 squared is 9/4, right? Which you could simplify if you want to, or keep it as 9/4. So that's that y value. And this final one, the x value is going to be, what am I talking about? 2.5 or 5/2, or 2.5. And to find that y value, that's going to be 5/2 squared, which is 25/4. Okay? So think about this. Each of these rectangles is 1 wide and y value height, which these are the y values. So to find the approximation of these areas, this first rectangle that I have over here, that is going to be 1 wide and 1/4 high. The second one is 1 wide and 9/4 high. And the third area of this rectangle is 1 wide and 25/4 high, right? Which gives me 35/4, which is 8.75. So this clearly gives us the better estimation of it, but I actually don't know if it's over or under because sometimes it's under, but then it goes over. But then it's like, this is under, but that's over. So it's not fitting it perfectly. So yeah, it's still kind of an issue because you can see low approximation was 5, over was 14. This is the closest, still not perfect, it's 8.75. So how can we get a better approximation, a more accurate one? How is this going to be better? And the idea is we're going to have to use more rectangles. In these problems, I'm only giving you 3. I'm only giving you 2. I'm only giving you a small amount of rectangles to use. If I said you could use infinite rectangles, you would have this perfect approximation. And that's really where we're going with this whole entire chapter. So sorry, spoiler alert, that's that. Okay, let's crush through because I'm talking way too long. Okay. Estimate the area under the curve for y equals 2 to the x power. Okay, yikes. Y equals 2 to the x power, it's exponential, so we start off at 1, and when I plug in 1, I get 2, and I plug in 2, I get 4, I plug in 3, I get 8. So it pretty much does this, right? So here's our curve for each one. You guys can copy that for each one. Okay. And I'll make these, I don't know, orange looks a little wacky. I'll make it look gray. Okay, so there's the curve. This curve, y equals 2 to the x, is all of those here. All right, and it wants you to practice using LRAM and MRAM and RRAM. So LRAM means that your rectangles have to touch the leftmost points. So that would be... Oh, from -1 to 3, great. So from this -1 point all the way to the 3 point. So it has to include the -1 point all the way to the 3 point and the -1 point. Okay, awesome. So this is great. So at -1, ooh, this is great. It has to touch the left point, which makes this rectangle. Oh, geez, I take that back. You're only doing 2 subintervals? Oh my gosh, that means I'm only getting 2 rectangles. Oh my Lord. So it has to split this area in only 2 different rectangles. So that would mean it has to touch here and go all the way to here. That's rectangle 1. And then it has to split into another rectangle that touches on the left from here to here. Oh, okay, so it's 2 rectangles only, not 3 like we were doing earlier, or 4. So it's just 2 rectangles. And I only know I use 2, and they're 2 wide because this is just 4 wide. So each one should be 2 and 2. Okay, awesome. Clearly, LRAM is an under for the situation. It's a great one. Now MRAM. So now it's only 2 rectangles, so there's going to be one that's 2 wide here, one that's 2 wide here, but it has to touch the graph in the middle. So that would be here. It'd be this, and it would be this, where it's touching the middle, and it has that. Okay? Kind of what I'm seeing, I don't know actually if it's over or under. I think this one is a little more under technically, just based on what I'm visualizing. But you have that, so that's great. And then finally, we have RRAM, which is going to be where it touches on the right-hand side in these 2 spots. So if I'm making 2 triangles or 2 rectangles where I have to touch on the right, that'd be here, and that would be here. And I would get these 2 rectangles. And that's clearly over, right? It's clearly over, okay? And these 2 rectangles, by the way, that's 2 by 2, so that's 4 plus 2 by 8, that's 16. So the area is 20 here. Nice. The area here is 1 by 2, so it's 2 plus 2 by 4, which is 8. So that area is 10. And this one's a little bit wacky because this is 2 by 2, which is 4, and that looks like a 2 by half. So it looks like 1. So that's an area 5. So you could see over, or sorry, under, probably under, and then totally going over. All right, so that's, again, using them in the right spot, where here the rectangles are touching on the left. Here the rectangles are touching the line in the middle. Here they're touching the function on the right. Okay, love it. All right, let's answer these. If a function is increasing, oh, this is so great. So if a function is increasing, that means it could look like this, or it could look like this, increasing. Okay, 2 different ways to increase. One increases slowly, one increases faster. Then technically, your LRAM will be the lowest. Your MRAM will be in the middle, and your RRAM will be the biggest. And the reason I say that is because look at this example here where we have an increasing graph. You could see my LRAM was my smallest. It was so under, it was 5. Versus my MRAM is somewhere in the middle, gives me an approximation of 10, and my RRAM goes over my graph and it makes it the largest thing, right? So this is the smallest, and this is the largest, which is cool. What's bad about this, though, is that you guys are probably thinking, oh, LRAM's always the smallest. You're like, boom, LRAM's smallest, RRAM's highest, life is good. Not true. Not true at all. We've been having increasing graphs. What happens if I have a decreasing graph? And I'll kind of show you guys this. A decreasing graph is going to look like this. So I have, it's either going down like this, or it's going down slowly or more quickly like this. So, for example, I'll just do a really quick LRAM and RRAM. If I did LRAM, wouldn't it look like this? Where now the LRAM is touching in the left corner. That's over. That's the highest now. Versus an RRAM is going to be like this now with the right corner touching. You guys see what I mean? So now that's going to be an under approximation because the right side triangles now are underneath it, and that's small. That's really low. Versus LRAM is above. So now if it's decreasing, RRAM is the smallest and LRAM is the highest. So it's kind of fun. So it depends on the situation, but that's pretty much what I got. Okay, I got 2 more pages. I know I've been talking for way too long, and I'm literally doing this during lunch, and I'm hungry, and I'm going to throw up. So I got like 10 minutes left. Oh, my God. Okay, here we go. Cars traveling with various velocities shown in the table below. Once again, assume miles per hour. And they tell you the time and the velocity, and they don't give you any chart, which kind of sucks. But it says, number 1, estimate the distance traveled from 0 to 12 hours. So start to beginning. Using RRAM, love it. So this is now using the right with 3 sub-intervals. So this is 3 rectangles. So look what you have up here. You have from 0 to 12. I need to split this into 3 different parts. That means I'm splitting it into groups of 4. So I'll kind of use red only here. So to split this into 3 even groups, that's 0 to 4, and then 4 to 8, and then 8 to 12. So I have these 3 even groups, right? Hopefully everyone's good with that. So each of these groups, now look at this, okay? Each of these groups are from 0 to 4 or 4 to 8 and 8 to 12, so they're 4 big. So every time I add my rectangles, which again is going to be like width times height and width times height plus width times height because there's 3 subintervals, okay? Each of these groups is from 0 to 4. It's 4 big. Every one of them is 4 big, 4 big. So these are all 4 because, again, this is the width from t equals 0 to 4. This is also 4 because it's the width from t equals 4 to 8. And this is also 4 because it's the width from t equals 8 to 12. So all my rectangles are 4 wide. The height is going to be the issue now. It's like, what's the height of this? Look at this. I just got points. Well, if I'm using RRAM, I'm using the rightmost height. So I need to go all the way to the right of each one, and I'm using 44 as my highest height of this rectangle. And over here on the next one, the highest height of that rectangle is 48. Right? It's the highest one. It's all the way to the right. Not high. I shouldn't say highest. It's all the way to the right. Because we don't know if it's going up or down. I take that back. And the highest height, not the highest, the most right height is over here is 18. That gives me my RRAM approximation. And if I add those 3 separate pieces up, that comes out to be 440 miles because we're talking about total distance traveled. That's 440 if I add this plus this plus this. Okay? That's using RRAM. That was all the right and using those right-hand numbers of each interval. Okay, that's where these came from. Hopefully no questions there. So that's that. Fantastic. Let's use a blue for LRAM now. So LRAM, remember, now this is left. I'm thinking all the way to the left. So now I'm using estimate the distance traveled from 0 to 12 with 4 subintervals. Yikes. 4 subintervals. So now not 3, 4. And I'm using LRAM. So to split these into 4, I need groups of 3 total. I need 4 different groups. 4 different groups of 3. So it's from here to here, 0 to 3. From 3 to 6. From 6 to 9. And from 9 to 12. Those are my 4 different groups now. So now, when I do this, width times height, plus width times height, plus width times height, each of these widths now is 3. Every rectangle is 3 wide. Again, comes from width of t equals 0 to 3. That's 3 wide. And that continues 3 to 6, 6 to 9, 9 to 12. Now, though, for LRAM, you're using the leftmost y value of that function. So now I'm using these, the leftmost ones, the 10, 38, 62, and the 41, right? Because, again, it's the leftmost part, leftmost for each section, okay? That comes out to be 453 miles. That one is awesome. Totally love using that one. So that's the left one, okay? And finally, the last one says 0 to 12 hours using MRAM. So now it's the middle, but now it's 6 intervals. So every interval needs to be 2 long since it's 12. So that's from like here to here, here to here, 2, 3, 4, 5, 6. And now we use the middle. So there's going to be 6 total parts now. So they're all 2 wide, but the first one's 22. The next one's 2 wide, but the middle is 38. The next one's 2 wide, but the middle is 51. And I continue this for all of them. 41. Plus 2 times 25. Love it. So there's these 6 intervals. 1, 2, 3, 4, 5, 6. Using the middle y value. And that came out to be 470 miles. Absolutely love that problem. That one is really super fun. So guys, I'm sorry. This took way too long. I'm going to stop here for today. I know there's one more page, which, again, if you want to try it, go for it. We will do that on my birthday. This is my B-Day problem. Yay. Can't wait. It's going to be so cute and fun. So anyways, if you have any questions, go back. You could pause the video at any point. You could always ask me what's up. But this is probably a really cool start to integration. I think you guys will love it. So any questions, just ask me. And I'll see you guys Tuesday on my birthday. Sorry this video was so long. Okay, love you guys. Bye.